Hey everyone, picture this for a moment. You step outside on a clear morning, look up, and see that brilliant blue dome stretching endlessly above you. That azure canopy feels eternal, doesn't it? Like it's always been there, painted across the heavens since time began. But here's something that might blow your mind. That blue sky you're staring at right now, that gorgeous cerulean backdrop to every sunset photo and childhood memory, didn't exist for most of Earth's history. In fact, for nearly 2 billion years, our planet had no blue sky at all. Before you get too comfortable with that thought, let me hit you with another one. The reason you can even take that breath you just took, the oxygen filling your lungs right now, was once the most toxic substance on Earth. A deadly poison that triggered the planet's first mass extinction and nearly wiped out all life as it existed. Yet somehow, that same lethal gas became the foundation for everything we know and love today. Tonight, we're diving deep into one of the most extraordinary transformations in Earth's history. An event so profound, so earth-shattering, that it literally rewrote the rules of life itself. We're talking about the Great Oxygenation Event, a revolution that began roughly 2.4 billion years ago when microscopic organisms decided to completely flip the script on what it meant to be alive. And I know what you're thinking. Microscopic organisms? Really? How dramatic could that possibly be? Well, buckle up, because these tiny blue-green rebels didn't just change the game. They obliterated it, rebuilt it from scratch, and in the process created the world that would eventually give rise to forests, animals, and yes, even us. So dim the lights, maybe grab something to drink, and let's take a journey back to when Earth was an alien world. A place where the sky wasn't blue, the air couldn't sustain complex life, and the oceans held secrets that would reshape everything. This isn't just a story about ancient microbes. This is the story of how our planet learned to breathe. Now, to truly understand what happened during the Great Oxygenation Event, we need to travel back to a time when Earth was almost unrecognizable. We're talking about a period roughly 3.5 billion years ago, when our planet looked nothing like the vibrant, oxygen-rich world we call home today. The atmosphere back then was a cocktail of methane, carbon dioxide, and nitrogen, with virtually no free oxygen floating around. None. We're talking about oxygen levels that were literally 0.001% of what they are today. Think about that for a moment. If you somehow found yourself transported back to that ancient Earth, you wouldn't just struggle to breathe. You'd be dead within minutes. The air itself would be completely alien to your lungs, which have evolved to depend on that precious 21% oxygen concentration we take for granted. But here's where it gets really fascinating. This wasn't some barren, lifeless wasteland we're describing. Life was absolutely thriving in those ancient seas. It just wasn't the kind of life you'd recognize. The dominant organisms were anaerobic bacteria, creatures that not only survived without oxygen, but actually found it toxic. These microscopic pioneers had figured out how to extract energy from sulfur compounds, methane, and other chemicals that would make modern life forms keel over instantly. The landscape itself tells a story that's hard to imagine. Without oxygen in the atmosphere, there was no ozone layer protecting the surface from harsh ultraviolet radiation. The land was essentially sterilized by cosmic rays, a rocky desert baked under an unforgiving sun. All the action, all the biological innovation was happening underwater in the relative safety of the oceans. And those oceans, they were nothing like what we see today. They were loaded with dissolved iron, giving them a greenish tint that would have looked almost alien under that methane haze sky. The iron stayed dissolved because there was no oxygen around to react with it and cause it to precipitate out. This detail becomes absolutely crucial to our story, but we'll get to that in a moment. The early atmosphere was also much richer in carbon dioxide, creating a powerful greenhouse effect that kept the planet warm despite the sun being roughly 25% dimmer than it is today. Methane, produced by early life forms called methanogens, added even more warming power to this atmospheric blanket. It was a delicate balance that allowed liquid water to exist and life to flourish in those iron-rich seas. But change was coming. Somewhere in those ancient oceans, a group of microorganisms was about to evolve a capability so revolutionary that it would transform not just life on Earth, but the very chemistry of the planet itself. These organisms were cyanobacteria, and they were about to discover something that would make them the most influential life forms in Earth's history. Around 3 billion years ago, give or take a few hundred million years, cyanobacteria evolved what scientists call oxygenic photosynthesis. Now, photosynthesis itself wasn't new. Other organisms had already figured out how to harness light energy to power their metabolism. But cyanobacteria did something different, something that had never been done before on our planet. They learned to use water as their electron source. This might sound like a minor technical detail, but it was absolutely game-changing. When you split water molecules to extract electrons, you're left with a waste product. That waste product is oxygen. For the first time in Earth's history, organisms were pumping free oxygen into the environment as a byproduct of their metabolism. At first, this didn't seem like a big deal. The early cyanobacteria were probably just scattered populations in shallow marine environments, releasing small amounts of oxygen into water that was loaded with iron and other chemicals that readily absorbed it. The oxygen was being consumed almost as fast as it was produced, keeping atmospheric levels essentially at zero. But cyanobacteria had stumbled upon something incredible. Oxygenic photosynthesis is remarkably efficient compared to other forms of metabolism available at the time. It allowed them to extract more energy from their environment, grow faster, and reproduce more successfully than their competitors. Slowly but surely, they began to spread. What's truly remarkable is that we can trace this evolutionary innovation with precision that would have seemed impossible just a few decades ago. Using advanced molecular techniques, scientists have determined that all modern cyanobacteria can be traced back to a common ancestor that evolved around 2.9 billion years ago. The ancestors of cyanobacteria had branched off from other bacteria around 3.4 billion years ago, with oxygenic photosynthesis likely evolving sometime in that window. But here's where the story gets really interesting. There's a massive gap between when cyanobacteria evolved the ability to produce oxygen and when that oxygen actually started accumulating in the atmosphere. We're talking about a delay of anywhere from 400 million to 800 million years. That's an almost incomprehensibly long time, longer than complex life has existed on our planet. So what was happening during all those hundreds of millions of years? Why wasn't the oxygen building up? The answer lies in what scientists call oxygen sinks, chemical reactions and processes that consumed oxygen as quickly as it was being produced. The biggest oxygen sink was probably iron dissolved in the ancient oceans. When oxygen molecules encountered iron, they reacted to form iron oxides, essentially rust. This chemical reaction was so efficient that it could absorb enormous amounts of oxygen without raising atmospheric levels at all. The oceans were like a massive chemical sponge, soaking up oxygen and locking it away in mineral form. Another major sink was methane in the atmosphere. When oxygen and methane meet in the presence of ultraviolet radiation, they react to form carbon dioxide and water. Since methanogens were still pumping methane into the atmosphere, this created another pathway for oxygen consumption that kept atmospheric levels low. But perhaps the most important factor was the availability of trace elements that cyanobacteria needed to thrive. Recent research has revealed that nickel played a crucial role in this story. Early methanogens required nickel as an enzyme cofactor, and as long as volcanic activity was supplying plenty of nickel to the oceans, methane production could keep pace with oxygen production. However, as Earth's crust cooled and volcanic activity decreased, the supply of volcanic nickel began to dwindle. This created a competitive advantage for cyanobacteria over methanogens. As nickel levels dropped and urea became more stable in seawater, cyanobacteria began to flourish on a scale never before seen. The stage was set for one of the most dramatic transformations in Earth's history. Cyanobacteria populations exploded across the ancient oceans, forming vast colonies that we can still see evidence of today in structures called stromatolites. These layered formations, built by successive generations of cyanobacterial mats, became some of the most prominent features of shallow marine environments. As these oxygen factories spread across the planet's surface waters, they began to overwhelm the chemical sinks that had been absorbing their waste product for hundreds of millions of years. The iron dissolved in seawater was the first to go. As oxygen levels rose, iron began to precipitate out of solution, forming layers of iron oxides that settled onto the seafloor. This process created some of the most distinctive rock formations in Earth's geological record, banded iron formations. These rocks, with their alternating layers of iron, rich and iron-poor material, tell the story of this ancient oxygenation event in remarkable detail. Each band represents a cycle of oxygen production and consumption, a chemical signature of the biological revolution that was reshaping our planet. The banded iron formations weren't just passive records of change. They were active participants in the transformation, serving as enormous oxygen sinks that had to be filled before atmospheric levels could begin to rise. Layer by layer, these formations locked away the evidence of cyanobacterial activity, creating a geological library that scientists can read today to understand exactly how and when our planet's atmosphere changed. But the iron wasn't infinite. As cyanobacteria continued to spread and multiply, producing ever greater quantities of oxygen, they eventually began to outpace even the massive iron sinks in the ancient oceans. The dissolved iron was becoming oxidized and precipitating out faster than new iron could be supplied by weathering and volcanic activity. And that's when everything changed. Around 2.4 billion years ago, the oxygen sinks finally became saturated. The chemical buffers that had been absorbing oxygen for hundreds of millions of years were overwhelmed. For the first time in Earth's history, free oxygen began to accumulate in the atmosphere. This wasn't a gradual, gentle transition. Recent research suggests that the Great Oxygenation event happened remarkably quickly, possibly within just 1 to 10 million years. That might sound like a long time, but in geological terms, it's practically instantaneous. The atmospheric composition of our planet was transformed in what amounts to a cosmic eye blink. The consequences were immediate and catastrophic for much of the life that existed at the time. Remember, most organisms on Earth had evolved in an oxygen-free environment. To them, oxygen wasn't the breath of life we know it as today. It was a highly reactive, corrosive poison that could damage their cellular machinery and genetic material. As oxygen levels rose, a massive die-off began. Countless species of anaerobic bacteria, organisms that had dominated Earth's biosphere for over 1 billion years, suddenly found themselves living in an environment that was toxic to their very existence. It was Earth's first mass extinction, though it's rarely counted among the famous extinction events because it happened so long ago and involved organisms that left little fossil evidence. The scale of this extinction was staggering. Isotope geochemistry data from ancient sulfate minerals suggests that the biosphere shrank by more than 80% during this period. Imagine that for a moment. 4 out of every 5 living organisms on the planet simply vanished, unable to adapt to the new oxygen-rich world that cyanobacteria had created. It was biological warfare on a planetary scale, though the cyanobacteria certainly hadn't intended to commit genocide. But here's the fascinating thing about life. It finds a way. While most anaerobic organisms perished, some managed to retreat to environments where oxygen couldn't reach them. They fled to the deep ocean depths, to underground caverns, to the sediments at the bottom of lakes and seas. These oxygen-free refuges became the last bastions of the old world. And remarkably, descendants of these ancient anaerobes still live there today. Meanwhile, something extraordinary was happening among the survivors. A few organisms discovered that this toxic waste product could actually be turned into an advantage. They evolved the ability to use oxygen in their own metabolic processes, developing what we now call aerobic respiration. This was a game changer of epic proportions. You see, aerobic respiration is incredibly efficient compared to the metabolic pathways that had dominated the anaerobic world. When you combine oxygen with organic molecules, you can extract roughly 18 times more energy than anaerobic processes could manage. Suddenly, these oxygen-breathing organisms had access to an energy source that was like rocket fuel compared to what had come before. These early aerobic organisms could grow faster, reproduce more quickly, and outcompete their anaerobic cousins in any environment where oxygen was present. They were the pioneers of a new biological era, one where energy was abundant and evolutionary possibilities exploded. The foundation was being laid for the complex, multicellular life that would eventually populate our planet. But the great oxygenation event wasn't just reshaping biology. It was fundamentally altering Earth's climate system in ways that would have profound consequences for millions of years to come. Remember all that methane that had been keeping the planet warm? Oxygen was about to take care of that too. Methane is an incredibly powerful greenhouse gas, roughly 25 times more effective at trapping heat than carbon dioxide. The early atmosphere had been loaded with methane produced by those ancient methanogens, and this methane blanket had been keeping Earth warm, despite the sun being significantly dimmer than it is today. But as oxygen levels rose, something dramatic started happening. Oxygen and methane don't play well together. In the presence of ultraviolet radiation from the sun, these two gases react to form carbon dioxide and water. Since carbon dioxide is a much weaker greenhouse gas than methane, this reaction effectively stripped away much of the atmosphere's heat-trapping ability. The planet's thermostat was being reset, and the new setting was much, much colder. The climate consequences were swift and severe. As methane levels plummeted and the greenhouse effect weakened, global temperatures began to drop. What followed was one of the most extreme climate events in Earth's history, a period that scientists call snowball Earth. Between 2.3 and 2.2 billion years ago, ice sheets advanced from the poles toward the equator, eventually covering most of the planet's surface. Picture this frozen world. Glaciers grinding across continents, ice sheets reflecting sunlight back into space, temperatures so cold that even tropical regions were locked in permafrost. It was a planetary ice age that lasted for millions of years, a direct consequence of the oxygen revolution that cyanobacteria had unleashed. The very organisms that had given Earth its oxygen had inadvertently plunged it into a cosmic freezer. This snowball Earth event was both a crisis and an opportunity. Many species that had managed to survive the initial oxygen poisoning now faced the challenge of extreme cold. But life, as it always does, adapted. Some organisms found refuge in volcanic hot springs or deep ocean vents where geothermal energy kept the water liquid. Others evolved antifreeze proteins or developed strategies for surviving in ice. More importantly, the snowball Earth period may have accelerated the evolution of more complex cellular structures. When resources are scarce and conditions are harsh, evolution tends to favor efficiency and cooperation. This period likely saw the development of more sophisticated cellular machinery, better DNA repair mechanisms, and possibly even the first experiments in cellular cooperation that would eventually lead to multicellular life. Meanwhile, the oxygen that had triggered this climate catastrophe was busy transforming the planet in other ways. As oxygen molecules rose into the upper atmosphere, they encountered high-energy ultraviolet radiation from the sun. This radiation split some oxygen molecules into individual atoms, which then recombined with other oxygen molecules to form ozone, a 3-atom variant of oxygen. This might seem like a minor chemical detail, But the formation of the ozone layer was absolutely crucial for life's future on Earth. Ozone is incredibly effective at absorbing ultraviolet radiation, the same radiation that had been sterilizing the planet's surface for billions of years. For the first time in Earth's history, a protective shield was forming in the atmosphere. This ozone layer didn't form overnight. It took millions of years for oxygen levels to build up sufficiently to create a substantial ozone shield. But once it was established, it fundamentally changed the rules of the game for life on Earth. Suddenly, the surface of the planet wasn't a radiation-blasted wasteland. It was potentially habitable real estate. The formation of banded iron formations continued throughout this period, creating some of the most spectacular geological records we have of the Great Oxygenation Event. These formations, with their distinctive red and black striped patterns, were being laid down on ocean floors around the world as iron continued to react with the newly abundant oxygen. Each layer tells a story of seasonal or cyclical changes in oxygen production. During periods of high biological activity, more oxygen was produced, leading to more iron precipitation and thicker bands of iron oxides. During quiet periods, less iron was deposited, creating thinner layers. These patterns have allowed scientists to reconstruct not just the timing of the oxygenation event, but also its rhythm and intensity. The banded iron formations also reveal something remarkable about the persistence of cyanobacteria during this turbulent period. Despite the climate chaos they had inadvertently triggered, these microorganisms continued to thrive and spread. They had found ecological niches that allowed them to survive even during the depths of snowball Earth, perhaps in areas where volcanic activity kept local environments warm enough for liquid water. As the snowball Earth period gradually came to an end, possibly triggered by volcanic carbon dioxide emissions that slowly rebuilt the greenhouse effect, the stage was set for the next phase of Earth's transformation. Oxygen levels continued to rise, though they fluctuated considerably over the following hundreds of millions of years. This wasn't a smooth, steady increase, but rather a series of rises and falls as the planet's chemical and biological systems adjusted to their new reality. Recent research has revealed that the Great Oxygenation Event wasn't actually a single event at all, but rather a series of oxygenation episodes spanning hundreds of millions of years. There were multiple whiffs of oxygen in Earth's atmosphere, temporary increases that were followed by decreases as various feedback mechanisms kicked in. It was a complex dance between biology, chemistry, and geology that played out over vast stretches of time. One of the most significant of these episodes occurred around 2.66 billion years ago, roughly 150 million years before the main oxygenation event. This earlier oxygen pulse lasted for less than 50 million years, but left clear chemical signatures in the rock record. It suggests that cyanobacteria had been experimenting with large-scale oxygen production much earlier than previously thought. These discoveries have revolutionized our understanding of Earth's early atmospheric evolution. Rather than a single dramatic transition, we now see the Great Oxygenation Event as a prolonged period of atmospheric instability, with oxygen levels fluctuating between pre- and post-oxygenation states for hundreds of millions of years. It was a planet learning to breathe, gasping and struggling as its atmospheric composition shifted back and forth. Throughout this extended period of change, cyanobacteria continued to be the dominant force shaping Earth's environment. Their colonies, preserved as stromatolites, became some of the most prominent features of shallow marine environments worldwide. These layered structures, built by successive generations of cyanobacterial mats, created underwater cities of microbes that could stretch for kilometers across ancient seabeds. The stromatolites weren't just passive structures, they were active ecosystems where different species of cyanobacteria specialized in different roles. Some were optimized for photosynthesis in bright shallow water. Others thrived in the dimmer conditions deeper in the mat. Some produced sticky compounds that helped bind sediment particles, while others secreted chemicals that could dissolve or precipitate minerals. These ancient microbial communities were incredibly sophisticated, displaying levels of cooperation and specialization that wouldn't be seen again until much more complex organisms evolved. They were the planet's first ecosystems, intricate webs of interaction between different species of bacteria that work together to transform their environment on a global scale. The success of these cyanobacterial communities was staggering. At their peak, around 1.25 billion years ago, stromatolites were among the most abundant life forms on Earth. They dominated shallow marine environments on every continent, creating biological landscapes unlike anything we see today. The planet was essentially covered in vast gardens of bacterial mats, all of them pumping oxygen into the atmosphere and fundamentally altering the chemistry of Earth's surface. But this golden age of stromatolites wouldn't last forever. As oxygen levels stabilized and new forms of life evolved to take advantage of the oxygen-rich environment, the dominance of cyanobacteria began to wane. By the time complex multicellular life appeared, stromatolites had declined to just 20% of their former abundance. Yet their legacy was permanent and profound. Every breath of oxygen-rich air, every blue sky, every complex organism that would ever live on Earth owed its existence to the metabolic innovations of these ancient microbes. They had not just survived the transition from an anaerobic to an aerobic world, they had engineered it. In doing so, they had set the stage for every major evolutionary innovation that would follow, from the first eukaryotic cells to the eventual emergence of plants, animals, and ultimately, us. The transformation wasn't happening in isolation. As cyanobacteria continued their relentless march across Earth's shallow seas, they were inadvertently writing the planet's geological history in stone. Those banded iron formations we mentioned earlier weren't just pretty rocks. They were becoming a permanent record of one of the most important biological revolutions in Earth's history, preserved layer by layer in what would become some of our planet's most valuable iron ore deposits. Think about that for a moment. The steel in your car, the iron in your blood, the metal framework of the skyscrapers around you, much of it originated from this ancient biological process. Every time you see rust forming on a piece of metal, you're witnessing the same chemical reaction that was transforming Earth's oceans 2.5 billion years ago. Oxygen meeting iron, creating the distinctive red compounds that would paint both our planet's rocks and its future. But the banded iron formations tell us something else that's absolutely fascinating. They reveal that oxygen production wasn't steady or predictable. Instead, it fluctuated in cycles that created those distinctive alternating layers. During peak growing seasons, when cyanobacterial mats were thriving in warm, nutrient-rich conditions, oxygen production would spike. More iron would precipitate out of the seawater, creating thick bands of rust-colored minerals. During quieter periods, perhaps when nutrients were scarce or temperatures dropped, oxygen production would slow down. The iron bands would be thinner, separated by layers of silica-rich sediment. These patterns, preserved in rocks around the world, give us an almost day-by-day account of how life was reshaping the chemistry of our planet's oceans. The precision of this geological record is remarkable. Scientists can examine these ancient formations and determine not just when oxygen levels were rising, but how quickly, how much, and even what seasonal patterns might have looked like billions of years ago. It's like reading a chemical diary written by the planet itself, documenting one of the most important transitions in its history. And those transitions were becoming more dramatic with each passing million years. As cyanobacterial colonies spread across the globe, they began to create positive feedback loops that accelerated their own success. More oxygen meant that certain toxic compounds were being oxidized and removed from the environment. This created cleaner, more favorable conditions for even more cyanobacterial growth. The colonies themselves were becoming more sophisticated too. What started as simple mats of bacteria were evolving into complex layered communities, with different species occupying different niches within the same stromatolite structure. Some cyanobacteria specialized in capturing light at the very surface, where photosynthesis was most efficient. Others adapted to the dimmer conditions deeper in the mat, developing enhanced light harvesting capabilities. Some species focused on producing the sticky compounds that held the entire structure together, creating a kind of biological cement that could bind sand grains and precipitate minerals. Others became specialists in nutrient cycling, breaking down dead cells and recycling essential elements back into the community. It was cooperation on a scale that wouldn't be matched until much more complex organisms evolved millions of years later. These ancient microbial cities weren't just surviving in the changing world they were creating, they were thriving. Stromatolites began appearing in every conceivable shallow water environment, from tropical lagoons to Arctic seas. They adapted to different salinity levels, different temperatures, different nutrient conditions. Wherever there was sunlight and water, cyanobacteria found a way to establish their oxygen-producing colonies. The diversity of these formations is staggering. Some stromatolites grew as simple, flat mats that carpeted the seafloor, like biological parking lots. Others developed into towering, pillar-like structures that rose several meters above the surrounding sediment. Some formed branching, tree-like shapes that created underwater forests of living rock. Each form represented a different strategy for capturing light, accessing nutrients, and defending against the occasional grazing organisms that were beginning to evolve. But perhaps the most remarkable thing about these ancient communities was their longevity. Individual stromatolite structures could continue growing for thousands, even millions of years. Generation after generation of cyanobacteria would live, die, and be incorporated into the growing formation, creating biological monuments that dwarfed anything we see in the modern world. The impact on ocean chemistry was becoming increasingly dramatic. As iron continued to precipitate out of seawater, the oceans were gradually shifting from their ancient greenish tint to something closer to the blue we recognize today. But this wasn't the crystal-clear blue of modern tropical seas. These waters were still laden with dissolved minerals and organic compounds that gave them a murky, soup-like quality. The pH of seawater was changing too. Cyanobacterial photosynthesis removes carbon dioxide from water, making it less acidic and more alkaline. This shift in ocean chemistry had cascading effects on mineral precipitation, nutrient availability, and the survival of other organisms. The cyanobacteria weren't just adding oxygen to the system, they were fundamentally altering every aspect of marine chemistry. Temperature patterns were shifting as well. The massive colonies of cyanobacteria were affecting local water temperatures through their metabolic activity and their influence on water circulation patterns. In some areas, dense mats of bacteria created warm, stagnant conditions perfect for their own growth. In others, their oxygen production triggered chemical reactions that absorbed heat, creating cooler microclimates. These local effects were beginning to add up to global changes. The planet's thermostat was being adjusted not just by the removal of methane from the atmosphere, but by countless smaller changes in ocean temperature, chemistry, and circulation patterns. Earth was becoming a fundamentally different world, one where biology was an active force in shaping climate rather than simply responding to it. The evidence of this transformation is written in rocks around the world, but nowhere is it more dramatic than in the formations found in places like Western Australia, South Africa, and the Canadian Shield. These ancient geological provinces preserve some of the most complete records of the Great Oxygenation Event, with banded iron formations that stretch for hundreds of kilometers and contain billions of tons of precipitated iron. When you stand in front of these formations today, you're looking at the fossilized remains of an ancient biological revolution. Each stripe of red iron oxide represents millions of tons of oxygen that was pumped into primordial seas by organisms so small you'd need a microscope to see them individually. It's a humbling reminder of how profoundly life can shape the physical world, even when that life exists at a microscopic scale. But the banded iron formations also tell us something troubling. Around 1.85 billion years ago, they suddenly disappear from the geological record. The process that had been depositing iron for nearly a billion years simply stopped. This wasn't because cyanobacteria had given up producing oxygen. If anything, they were more successful than ever. The formation stopped because there was no more iron left to precipitate. The oceans had been stripped clean of their dissolved iron inventory. Every atom of iron that could react with oxygen had already done so, creating the massive ore deposits that would later fuel human civilization. But at the time, this represented a crucial tipping point. The last major oxygen sink had been eliminated. From now on, any oxygen produced by cyanobacteria would have nowhere to go except into the atmosphere. This moment, around 1.85 billion years ago, marks what scientists consider the end of the great oxygenation event proper and the beginning of a new phase in Earth's atmospheric evolution. Oxygen levels began to rise more steadily, though they were still far below modern concentrations. The planet was entering what geologists call the boring billion, a period of relative stability that would last for nearly a billion years, but calling it boring is misleading. This was actually a time of incredible innovation and preparation for what was to come. With oxygen levels stabilized and the worst of the climate chaos behind them, life began experimenting with entirely new ways of existing. The groundwork was being laid for cellular complexity that would eventually lead to plants, animals, and every form of life we recognize today. The cyanobacteria themselves were far from done with their planetary makeover project. While the massive banded iron formations were no longer being deposited, oxygen production continued at a steady pace. The atmosphere was gradually accumulating this life-giving gas, building toward concentrations that would support increasingly complex forms of metabolism. More importantly, that protective ozone layer was continuing to strengthen. With each passing million years, more oxygen was rising into the stratosphere, where ultraviolet radiation could split it into ozone molecules. This invisible shield was making the surface of the planet increasingly habitable, setting the stage for life's eventual colonization of the land. The chemical signatures of this ongoing oxygenation are preserved in different types of rock formations that replaced the banded iron deposits. Red sandstones, colored by iron oxides, began appearing in the geological record. These red beds represent a new type of chemical weathering that could only occur in an oxygen-rich atmosphere. When iron-bearing minerals on land were exposed to oxygen and water, they rusted, creating the distinctive red coloration that we still associate with desert landscapes today. The appearance of these red beds marked another milestone in Earth's transformation. For the first time in the planet's history, the surface environment was oxidizing. Rocks were being weathered by oxygen-rich rainwater, soils were developing new mineral compositions, and the very chemistry of the land surface was being rewritten by the atmospheric changes that cyanobacteria had initiated. Meanwhile, in the oceans, new types of organisms were beginning to appear. Some had evolved sophisticated mechanisms for dealing with oxygen toxicity, developing enzymes that could neutralize the harmful byproducts of aerobic metabolism. Others had gone a step further, learning to harness oxygen's reactive power for their own energy production. These early aerobic organisms were still microscopic, but they represented a fundamental shift in how life could operate on Earth. Instead of struggling to survive in an oxygen-contaminated world, they were thriving because of it. They could extract far more energy from their food than their anaerobic ancestors, allowing them to grow faster, reproduce more efficiently, and explore new ecological niches. The success of these oxygen-breathing organisms created new evolutionary pressures that drove innovation in cellular design. Cells began developing more sophisticated internal structures, better DNA repair mechanisms, and improved systems for managing energy production. The foundation was being laid for the kind of complex cellular architecture that would eventually make multicellular life possible. But perhaps the most significant development was happening in the realm of cellular cooperation. Some organisms began experimenting with partnerships, temporary alliances that allowed different species to share resources and divide labor. These early symbiotic relationships were crude compared to what would come later, but they represented the first tentative steps toward the kind of cellular cooperation that would eventually create plants and animals. The atmospheric oxygen concentration was still climbing, though much more slowly than during the initial oxygenation event. Current estimates suggest that by the end of the boring billion, oxygen levels had reached perhaps 10% of modern atmospheric concentrations. This was still far below the 21% we breathe today, but it was more than enough to support increasingly sophisticated forms of life. The planet's climate was also stabilizing after the dramatic swings of the early oxygenation period. The snowball Earth episodes were becoming less frequent and less severe as the atmosphere developed better buffering mechanisms. Oxygen and ozone were creating new chemical pathways that helped regulate temperature and atmospheric composition. This climate stability was crucial for the continued evolution of life. Extreme environmental fluctuations tend to favor simple, hardy organisms that can survive dramatic changes. More stable conditions allow for the evolution of complex, specialized organisms that are adapted to specific environmental niches. The stage was being set for an explosion of biological diversity that would reshape the planet once again. The cyanobacteria that had started this whole revolution were also continuing to evolve and diversify. Different species adapted to different environments, from the shallowest tide pools to the deepest parts of the photic zone, where sunlight could still penetrate. Some developed enhanced UV protection to survive in the increasingly ozone-depleted surface waters. Others evolved improved nutrient scavenging abilities to compete in environments where resources were becoming scarce. The stromatolites they built became increasingly diverse and sophisticated. Some formations developed elaborate internal structures that optimized light capture and nutrient flow. Others evolved defensive mechanisms to protect against the grazing organisms that were beginning to appear in greater numbers. The ancient microbial cities were becoming more like modern ecosystems, with complex webs of interaction between different species and environmental factors. Yet even as life was becoming more complex and diverse, the fundamental importance of cyanobacteria never diminished. They remained the primary producers of oxygen, the organisms responsible for maintaining the atmospheric composition that made all other life possible. Without their continued photosynthetic activity, the oxygen levels that had been so hard won would gradually decline as geological processes consumed oxygen faster than it could be replaced. This dependence on photosynthetic organisms for atmospheric oxygen continues to this day. Every second breath you take comes from oxygen produced by photosynthesis. Whether from cyanobacteria in the oceans, trees in forests, or phytoplankton in marine ecosystems. The biological revolution that began 2.5 billion years ago is still ongoing, still shaping our planet's atmosphere with every photosynthetic reaction. The Great Oxygenation Event had fundamentally altered the trajectory of life on Earth. What began as a metabolic innovation in microscopic organisms had cascaded into planetary transformation on a scale that's difficult to comprehend. The chemistry of the oceans, the composition of the atmosphere, the mineral content of rocks, the color of the sky, all had been changed by the activities of organisms too small to see with the naked eye. But the story was far from over. The oxygen-rich world that cyanobacteria had created was about to give rise to forms of life that would have been impossible in the ancient anaerobic oceans. Complex cells with sophisticated internal structures, multicellular organisms with specialized tissues, and eventually, the kinds of large, active organisms that we think of as typical life forms today. The blue-green revolutionaries had done their work. They had poisoned the ancient world and built a new one from its ashes. They had turned a reducing planet into an oxidizing one, a methane-hazed world, into one with crystal clear skies. Most importantly, they had created the conditions that would allow life to explore possibilities that had never existed before in Earth's history. The sky was turning blue, one oxygen molecule at a time, and with that transformation, our planet was becoming the world we know today. A place where complex life could flourish under the protection of an ozone layer, powered by the energy-rich chemistry of aerobic metabolism and surrounded by the azure beauty of an oxygen-scattered sky. The transformation happening in Earth's atmosphere wasn't just changing the chemistry of air and water, it was rewriting the fundamental rules of what life could become. As oxygen levels continued their slow but steady climb, something extraordinary began happening in the microscopic world that would set the stage for every complex organism that would ever exist. Around 2 billion years ago, give or take a few 100 million years, some of those early oxygen-breathing organisms began experimenting with something that had never been tried before in Earth's history. Instead of simply coexisting as separate cells floating in the ancient seas, they started forming partnerships. Not temporary alliances or casual cooperation, but permanent mergers that would create entirely new types of living things. These weren't the cyanobacteria that had started the oxygen revolution. Those blue-green pioneers were still thriving, still pumping out their chemical waste product, still building their massive stromatolite cities across the shallow seas. But other organisms, ones that had learned to not just tolerate oxygen, but actually use it for energy production, were about to take evolution in a direction that would have been impossible in the old anaerobic world. The process probably started simple enough. One cell engulfing another, perhaps as a predatory act, or maybe just an accident of cellular mechanics. But instead of digesting its captive, something remarkable happened. The engulfed cell survived inside its host, creating a partnership that benefited both organisms. The host cell provided protection and resources, while the captured cell contributed specialized capabilities that the host lacked. This process, which scientists call endosymbiosis, had probably been attempted countless times in Earth's history. But the oxygen-rich environment created by cyanobacteria made these cellular partnerships not just possible, but incredibly advantageous. Oxygen-breathing bacteria that found themselves living inside other cells could provide their hosts with far more energy than had ever been available before. Think about the math for a moment. Anaerobic metabolism, the kind that had dominated Earth for over 1 billion years, could extract maybe 2 units of energy from a sugar molecule. Aerobic respiration, powered by oxygen, could extract 38 units of energy from that same molecule. Any organism that could harness this oxygen-powered energy production would have an enormous advantage over its purely anaerobic competitors. These early endosymbiotic partnerships were crude compared to what would come later. The cellular machinery for managing such arrangements was still being invented through trial and error. Many attempts probably failed, ending in the death of one or both partners. But the ones that worked, they worked spectacularly well. The successful partnerships began to spread and diversify. Some captured cells specialized in energy production, becoming what we now recognize as the ancestors of mitochondria, the powerhouses that drive energy production in almost every complex cell today. Others focused on different tasks, like managing waste products or processing specific types of nutrients. But perhaps the most important partnership involved cyanobacteria themselves. Some early cells managed to capture and maintain living cyanobacteria as internal partners. These captured cyanobacteria continued doing what they did best, harvesting light energy and producing oxygen, but now they were doing it as part of a larger cellular community rather than as independent organisms. These cyanobacterial captives would eventually evolve into chloroplasts, the green structures that power photosynthesis in plants and algae today. Every leaf that turns sunlight into sugar, every blade of grass that grows in your yard, every tree that produces the oxygen you breathe, They're all powered by the descendants of ancient cyanobacteria that were captured and domesticated by other cells nearly 2 billion years ago. The emergence of these complex cells, which scientists call eukaryotes, represented a quantum leap in biological sophistication. Unlike the simple prokaryotic cells that had dominated Earth's early history, eukaryotes had internal compartments, specialized structures, and the ability to manage multiple different types of metabolism within a single cell. More importantly, they had something that would prove absolutely crucial for the future evolution of complex life. They had a nucleus, a membrane-bound compartment that protected and organized their genetic material. This might seem like a minor organizational detail, but it opened up possibilities for genetic innovation that had never existed before. With their DNA safely tucked away in a protected nucleus, eukaryotic cells could experiment with much larger, more complex genomes. They could develop sophisticated gene regulation systems that allowed them to respond to environmental changes in ways that prokaryotes never could. They could even begin the process of sexual reproduction, mixing and matching genetic material between different individuals to create offspring with novel combinations of traits. But the real game changer was energy. Those captured oxygen-breathing bacteria were providing eukaryotic cells with energy budgets that dwarfed anything available in the anaerobic world. With abundant energy at their disposal, these cells could afford to maintain complex internal structures, support larger cell sizes, and engage in energy-expensive activities like active movement and rapid growth. The fossil record from this period is frustratingly sparse. Soft-bodied microscopic organisms don't preserve well, and most of our evidence for early eukaryotic evolution comes from chemical signatures in ancient rocks rather than actual fossils. But those chemical clues paint a picture of biological innovation on a scale that hadn't been seen since the origin of life itself. Styrene molecules, chemical fossils produced by eukaryotic cells, begin appearing in rocks around 2.7 billion years ago. These molecular signatures tell us that complex cells were already experimenting with sophisticated membrane systems and sterile-based chemistry that would later become essential for multicellular life. The timing is significant. These early eukaryotes were appearing just as the Great Oxygenation Event was reaching its peak intensity. They weren't just benefiting from the oxygen-rich environment that cyanobacteria had created. They were among its first and most successful exploiters, organisms that could thrive in conditions that were still toxic to most life on Earth. As oxygen levels continued to climb throughout the Proterozoic eon, eukaryotic cells began diversifying into forms that would have seemed almost alien compared to the simple bacteria that had preceded them. Some developed elaborate internal structures that looked like microscopic cities, with specialized districts for different cellular functions. Others experimented with external appendages, whip-like flagella that allowed them to swim actively through the water, rather than simply drifting with the currents. Size became a major frontier for innovation. While prokaryotic cells were typically measured in micrometers, eukaryotes began pushing into size ranges that were orders of magnitude larger. Some developed into single cells that were visible to the naked eye, massive organisms by microbial standards that could dominate their local environments through sheer physical presence. But size brought new challenges. Larger cells needed more sophisticated systems for managing nutrients, waste products, and internal transport. They needed stronger structural frameworks to maintain their shape and integrity. Most importantly, they needed better ways to manage the increased genetic complexity that came with their expanded capabilities. Sexual reproduction emerged as one solution to these challenges. By combining genetic material from two different individuals, eukaryotic cells could generate offspring with novel combinations of traits while also purging harmful mutations that might accumulate in asexual lineages. This process added a new dimension to evolution, allowing beneficial traits from different lineages to be combined in ways that had never been possible before. The implications were staggering. Sexual reproduction meant that evolution could now proceed through recombination as well as mutation. Favorable traits could spread through populations much more rapidly, and organisms could adapt to environmental changes with unprecedented speed and precision. The stage was being set for evolutionary arms races and adaptive radiations that would reshape the biosphere repeatedly over the coming billions of years. Meanwhile, the atmospheric oxygen concentration was approaching levels that would support even more energy-intensive forms of life. Current estimates suggest that by around 1.5 billion years ago, oxygen levels had reached perhaps 15 to 20% of modern atmospheric concentrations. This was getting close to the threshold where large, active, multicellular organisms could maintain the high metabolic rates needed for complex behaviors and sophisticated body plans. The ozone layer was also reaching maturity. With oxygen levels high enough to support substantial ozone production in the stratosphere, Earth's surface was finally becoming a truly habitable environment. The harsh ultraviolet radiation that had sterilized the continents for billions of years was being filtered out by an increasingly effective atmospheric shield. For the first time in Earth's history, life had the option of leaving the oceans. The land surface, once a barren wasteland baked by cosmic radiation, was becoming a potential frontier for biological colonization. It would still be hundreds of millions of years before complex organisms would actually make that transition, but the possibility was now written into the planet's atmospheric chemistry. The success of eukaryotic cells was creating new evolutionary pressures that drove further innovation. Competition between these complex organisms led to the development of more sophisticated survival strategies. Some became predators, developing cellular machinery for capturing and consuming other cells. Others became more efficient at finding and processing nutrients from their environment. Defense mechanisms evolved in response to predation pressure. Some cells developed thick protective walls or toxic compounds that made them unpalatable to predators. Others adopted strategies like rapid reproduction or the ability to form protective aggregations when threatened. These aggregations were particularly interesting because they represented the first tentative steps toward multicellularity. When individual cells began sticking together for mutual benefit, they were experimenting with the kind of cellular cooperation that would eventually lead to plants, animals, and fungi. The transition from single-celled to multicellular life wasn't a sudden leap. It was a gradual process that probably began with simple cell colonies, where individual cells remained largely independent but gained some advantages from being part of a larger group. Over time, some colonies began developing specialized cells that performed different functions for the group as a whole. This division of labor was another revolutionary innovation made possible by the energy abundance of the oxygen-rich world. In the old anaerobic environment, every cell had to be capable of performing all the functions necessary for survival. There simply wasn't enough energy available to support specialists that depended on other cells for basic needs. But with aerobic metabolism providing energy budgets that were an order of magnitude higher, cellular specialization became not just possible, but advantageous. Some cells could focus entirely on photosynthesis, others on defense, still others on reproduction or structural support. The efficiency gains from this division of labor more than compensated for the costs of maintaining non-independent cells. The earliest multicellular organisms were probably simple sheets or filaments of cells, not much more complex than modern bacterial mats. But they were fundamentally different from bacterial communities because their cells were genetically identical and developmentally coordinated. They were true individuals made up of cooperating parts rather than collections of independent organisms. These early experiments in multicellularity were setting the stage for one of the most dramatic evolutionary transitions in Earth's history. Within a few 100 million years, some of these simple multicellular organisms would begin developing the sophisticated body plans and complex tissues that would eventually give rise to the familiar plants and animals of the modern world. But that explosion of complex life was still far in the future. For now, Earth was populated primarily by microscopic organisms, most of them still single-celled, living in oceans that were gradually becoming more familiar in their chemistry and temperature patterns. The planet was in a kind of biological adolescence, having outgrown its simple prokaryotic childhood, but not yet ready for the full complexity of macroscopic life. The cyanobacteria that had started this whole transformation were still thriving, still building their massive stromatolite formations, still pumping oxygen into an atmosphere that was finally capable of sustaining the gas in substantial concentrations. Their success had created the conditions for their own eventual marginalization, as more complex organisms began to outcompete them in many environments. But their legacy was permanent and profound. Every molecule of oxygen in the atmosphere, every red iron formation in ancient rocks, every complex cell with mitochondria and chloroplasts, all bore witness to the metabolic innovation that had transformed a reducing planet into an oxidizing one. The transformation of Earth's atmosphere was essentially complete. Oxygen levels would continue to fluctuate over the coming billions of years, sometimes rising higher than modern concentrations, sometimes falling to levels that would challenge complex life. But the fundamental character of Earth's atmospheric chemistry had been permanently altered. Never again would our planet return to the methane-hazed, iron-rich world that had existed before the cyanobacterial revolution. The blue-green rebels had not just changed the game, they had created an entirely new game, one where energy was abundant, where chemical possibilities were expanded, and where life could explore levels of complexity that had been unimaginable in the ancient anaerobic world. The sky was blue now, scattered by oxygen molecules that absorbed and re-radiated light in ways that painted the atmosphere in shades of azure and cerulean. It was a color that had never existed in Earth's early history, a visual signature of the biological revolution that had transformed our planet from an alien world into the oxygen-rich biosphere we call home. And in that blue sky, invisible to any observer who might have been watching, ozone molecules were quietly performing their crucial task of filtering out harmful radiation. The protective shield that would eventually allow life to colonize the land was reaching maturity, powered by the same oxygen that cyanobacteria had been producing as waste for over 1 billion years. The stage was set for the next chapter in Earth's biological history. Complex cells with sophisticated internal machinery were diversifying into forms that would eventually give rise to every major group of organisms we recognize today. Multicellular life was beginning to experiment with the kinds of tissue organization and developmental complexity that would make large, active organisms possible. But perhaps most importantly, the planet had learned to breathe. The chemical cycles that regulate atmospheric composition, the biological processes that maintain oxygen levels, the intricate feedback mechanisms that keep our atmosphere within the narrow range that can support complex life, all had their origins in the metabolic activities of microscopic organisms that had lived and died billions of years before complex life even existed. The Great Oxygenation Event wasn't just ancient history, it was the foundation upon which every breath you take, every blue sky you admire, every moment of your existence ultimately depends. The blue-green revolutionaries had given Earth its breath, and in doing so, they had made every subsequent chapter of the planet's biological story possible. The oxygen was flowing freely now, no longer consumed as quickly as it was produced, no longer trapped in chemical sinks or locked away in mineral formations. It was accumulating in the atmosphere, building toward concentrations that would support increasingly sophisticated forms of life, creating the chemical foundation for a world where complexity could flourish. And with that accumulation, Earth was becoming recognizably modern in its atmospheric composition, even as its biological inhabitants remained almost entirely microscopic. The planet was poised on the brink of another transformation, one that would eventually fill its blue skies with flying organisms, its oxygen-rich atmosphere with the sounds of complex life, and its ozone-protected surface with the footsteps of creatures that could never have survived in the ancient anaerobic world. But those developments lay hundreds of millions of years in the future. For now, Earth was content to breathe its new oxygen-rich atmosphere, to bask under its protective ozone layer, and to nurture the microscopic communities that were quietly preparing for the next great leap in the complexity of life. The revolution was complete, but the story was just beginning. The numbers are staggering when you really think about them. We're talking about oxygen levels that climbed from essentially zero to roughly 10% of modern atmospheric concentrations over the course of several 100 million years. That might sound gradual, but in geological terms, it was breathtakingly rapid. And the consequences of this atmospheric revolution were about to cascade through every aspect of life on Earth in ways that would have been impossible to predict. By around 2 billion years ago, something remarkable was happening in the microscopic world of early eukaryotic cells. These complex organisms, powered by their captured oxygen-breathing bacteria, were beginning to push the boundaries of what single-celled life could accomplish. Some were growing to sizes that dwarfed their prokaryotic ancestors, becoming cellular giants that could dominate their local environments through sheer physical presence. Others were experimenting with shapes and structures that had never existed before. Elaborate internal scaffolding systems, intricate membrane networks, specialized compartments for different cellular functions. It was like watching microscopic architecture evolve in real time, with each innovation building on the last to create increasingly sophisticated cellular designs. But perhaps the most significant development was happening at the genetic level. These early eukaryotes weren't just larger and more complex than their predecessors. They were also becoming more genetically flexible, more capable of rapid evolutionary change. Sexual reproduction was spreading through eukaryotic populations, creating new possibilities for genetic recombination that would accelerate evolution in ways the prokaryotic world had never experienced. The implications were profound. In the old anaerobic world, evolution had been primarily driven by random mutations, a slow and often inefficient process. But sexual reproduction introduced the possibility of combining beneficial traits from different lineages, allowing favorable characteristics to spread through populations much more rapidly than had ever been possible before. This genetic flexibility was becoming crucial because the environment was still changing. Oxygen levels continued to fluctuate, sometimes rising to concentrations that approached modern levels, other times dropping back toward the barely detectable concentrations of earlier eras. These atmospheric swings created intense evolutionary pressure, favoring organisms that could adapt quickly to changing conditions. The geological record from this period tells a story of remarkable environmental instability. Chemical signatures in ancient rocks reveal multiple episodes of atmospheric oxygenation, followed by periods of decline. It wasn't a smooth, steady progression toward modern oxygen levels, but rather a series of advances and retreats that played out over hundreds of millions of years. Each of these atmospheric fluctuations triggered evolutionary responses that pushed life in new directions. During high oxygen periods, organisms could afford to experiment with energy-expensive innovations like larger cell sizes, more complex internal structures, and more active lifestyles. During low oxygen episodes, survival favored efficiency and the ability to extract maximum energy from limited resources. This cycle of environmental pressure and evolutionary response was creating a kind of biological arms race. Organisms that could better tolerate oxygen fluctuations had advantages over those that were adapted to narrow environmental ranges. Competition intensified, driving the development of more sophisticated survival strategies and more efficient metabolic systems. Meanwhile, the global distribution of oxygen was becoming increasingly complex. Different marine environments developed different oxygen concentrations based on local factors like water temperature, nutrient availability, and biological activity. This environmental heterogeneity created opportunities for evolutionary specialization, with different organisms adapting to different oxygen niches. Some eukaryotic cells thrived in the highly oxygenated surface waters, where photosynthetic activity was highest. Others specialized in the oxygen-poor depths, where conditions more closely resembled the ancient anaerobic world. Still others became generalists, capable of functioning across a wide range of oxygen concentrations. This ecological diversification was laying the groundwork for increasingly complex biological communities. Instead of the relatively simple microbial mats that had dominated earlier eras, marine ecosystems were developing multiple trophic levels with different organisms filling different ecological roles. Predation was becoming a major evolutionary force for the first time in Earth's history. In the energy-limited anaerobic world, organisms had primarily competed for resources rather than actively hunting each other. But the energy abundance of aerobic metabolism made predatory lifestyles not just possible, but highly successful. Early eukaryotic predators developed sophisticated cellular machinery for capturing and consuming other cells. Some evolved flexible cell membranes that could engulf prey much larger than themselves. Others developed chemical weapons, toxic compounds that could paralyze or kill their victims. The evolutionary response was equally dramatic, with prey organisms developing defensive mechanisms ranging from protective shells to rapid escape behaviors. This predator-prey dynamic was driving innovation at an unprecedented pace. Arms races between hunters and hunted led to increasingly sophisticated cellular technologies, more efficient energy production systems, and more complex behavioral repertoires. The microscopic world was becoming a battlefield where survival depended on constant innovation and adaptation. The success of these early complex cells was also beginning to affect global biogeochemical cycles in new ways. Unlike the cyanobacteria that had dominated earlier eras, eukaryotic organisms were capable of much more diverse metabolic strategies. Some were photosynthetic, others were purely heterotrophic, and still others combined multiple metabolic pathways within single cells. This metabolic diversity was creating new patterns of nutrient cycling that affected everything from ocean chemistry to atmospheric composition. Elements like nitrogen, phosphorus, and sulfur were being processed through biological systems in ways that had never occurred before, creating feedback loops that influenced global environmental conditions. The carbon cycle was undergoing particularly dramatic changes. Eukaryotic cells were capable of producing much more complex organic molecules than their prokaryotic predecessors, and they were also more efficient at breaking down organic matter. This was affecting both the burial of organic carbon in sediments and the release of carbon dioxide back to the atmosphere. These biogeochemical innovations were helping to stabilize Earth's climate system in new ways. The planet was developing more sophisticated mechanisms for regulating atmospheric composition, temperature, and ocean chemistry. Instead of the wild swings that had characterized earlier periods, environmental conditions were becoming more buffered and predictable. This environmental stability was crucial for the continued evolution of complex life. Extreme fluctuations tend to favor simple, hardy organisms that can survive dramatic environmental changes. More stable conditions allow for the evolution of sophisticated, specialized organisms that are adapted to specific ecological niches. By around 1.5 billion years ago, Earth's biosphere was beginning to look fundamentally different from anything that had existed before. The oceans were populated by diverse communities of eukaryotic organisms, many of them large enough to be visible without microscopy. These weren't the simple bacterial films that had carpeted earlier seas, but complex three-dimensional ecosystems with multiple species interacting in sophisticated ways. Some of these early eukaryotic communities were beginning to experiment with multicellularity, forming aggregations of cells that functioned as integrated units rather than collections of independent individuals. These early multicellular organisms were simple by modern standards, often consisting of just a few dozen or a few hundred cells organized into basic structures. but they represented a fundamental breakthrough in biological organization. For the first time in Earth's history, individual cells were sacrificing their independence for the benefits of group membership. Some cells specialized in reproduction, others in feeding, still others in defense or structural support. This division of labor allowed multicellular organisms to achieve capabilities that were impossible for single cells. The transition to multicellularity wasn't happening in isolation. It was being driven by the same evolutionary pressures that were shaping the rest of the eukaryotic world, particularly the intense competition for resources and the constant threat of predation. Organisms that could function as coordinated groups had significant advantages over those that remained strictly single-celled. Multicellular organization also opened up new possibilities for size and complexity. While single cells are limited by surface area to volume ratios and diffusion constraints, multicellular organisms can grow much larger while maintaining efficient internal transport systems. This size advantage was particularly important in competitive environments where physical dominance could determine survival. The earliest multicellular organisms were probably simple sheets or filaments of cells, similar to some modern algae and fungi. But even these basic forms represented revolutionary innovations in biological organization. They required new mechanisms for cell-to-cell communication, coordinated development, and integrated metabolism. More importantly, they required new genetic systems for controlling cellular differentiation and tissue organization. The evolution of multicellularity wasn't just about cells sticking together. It was about developing the regulatory mechanisms that could coordinate the activities of hundreds or thousands of individual cells into a single functional organism. These regulatory systems were becoming increasingly sophisticated as multicellular organisms diversified and grew more complex. Gene networks that controlled development, signaling pathways that coordinated cellular activities, and feedback mechanisms that maintained tissue organization were all evolving rapidly in response to the opportunities and challenges of multicellular life. The fossil record from this period is frustratingly incomplete, but the chemical signatures preserved in ancient rocks tell a story of remarkable biological innovation. Steroid molecules produced by complex eukaryotic cells become increasingly common and diverse, suggesting that these organisms were experimenting with sophisticated membrane systems and cellular architectures. Isotope ratios in ancient organic matter reveal changes in metabolic pathways and ecological relationships that point to increasingly complex biological communities. The simple, relatively uniform ecosystems of earlier eras were giving way to diverse, structured communities with multiple trophic levels and sophisticated ecological interactions. Perhaps most remarkably, some of these early multicellular organisms were beginning to produce mineralized structures, hard parts that could be preserved in the fossil record. These weren't the elaborate shells and skeletons that would characterize later multicellular life, but they were the first tentative steps toward the kind of structural innovation that would eventually produce complex body plans. The ability to precipitate minerals was another innovation made possible by the oxygen-rich environment that cyanobacteria had created. Many biomineralization processes require or are enhanced by oxidizing conditions, and the increasingly oxygenated oceans were providing ideal conditions for organisms to experiment with hard part production. These mineralized structures served multiple functions. Some provided protection against predators, others offered structural support for larger body sizes, and still others created specialized tools for feeding or locomotion. Each innovation opened up new ecological possibilities and drove further evolutionary diversification. The success of early multicellular organisms was creating new evolutionary pressures that would drive even more dramatic innovations in the future. Competition between multicellular groups led to increasingly sophisticated survival strategies, more efficient resource utilization, and more complex ecological interactions. But perhaps the most important consequence of multicellular evolution was the potential it created for even larger and more active organisms. The basic body plans and developmental mechanisms that were evolving during this period would eventually give rise to all the major groups of complex life that populate Earth today. By around 1 billion years ago, Earth's biosphere had been fundamentally transformed from its ancient anaerobic origins. The oceans contained diverse communities of single-celled and multicellular eukaryotes, many of them large enough to be seen with the naked eye. These organisms were engaged in complex ecological relationships that included predation, competition, cooperation, and symbiosis. The atmosphere contained oxygen concentrations that approached modern levels, at least during some periods. This oxygen-rich atmosphere supported increasingly active and energy-intensive lifestyles, allowing organisms to maintain high metabolic rates and engage in sophisticated behaviors that would have been impossible in the energy-limited anaerobic world. The ozone layer had reached sufficient density to provide effective protection against harmful ultraviolet radiation. For the first time in Earth's history, the surface of the planet was becoming truly habitable, setting the stage for life's eventual colonization of terrestrial environments. Yet despite all these innovations, life remained primarily microscopic and marine. The dramatic visible organisms that would eventually populate Earth's oceans, land surfaces, and atmosphere were still hundreds of millions of years in the future. The biological revolution initiated by cyanobacteria had created the conditions necessary for complex life, but the full realization of that potential would require additional evolutionary breakthroughs. The foundations were in place, though. Oxygen-powered metabolism, eukaryotic cellular organization, sexual reproduction, multicellular development, and mineralized hard parts were all evolutionary innovations that would prove essential for the emergence of plants, animals, and fungi. The stage was set for the next great chapter in Earth's biological history, but that story would have to wait. For now, Earth was content to nurture its microscopic communities in oxygen-rich seas under an increasingly blue sky. The planet had learned to breathe, and that breath was supporting levels of biological complexity that would have been unimaginable in the ancient anaerobic world. The Great Oxygenation Event had done its work. What had begun as the metabolic innovation of microscopic cyanobacteria had cascaded through Earth's entire system, transforming the chemistry of the atmosphere and oceans, the color of the sky, the mineral composition of rocks, and the very nature of life itself. Every breath of oxygen-rich air, every glimpse of blue sky, every moment of complex life on our planet could be traced back to those ancient blue-green revolutionaries that had dared to split water molecules and release their toxic waste into the environment. They had poisoned the anaerobic world and built a new one from its ashes, creating the chemical foundation for every subsequent chapter in Earth's biological story. The sky was blue now, painted by the same oxygen molecules that powered the metabolism of increasingly sophisticated organisms. And in that blue sky, invisible but essential, ozone molecules continued their quiet work of filtering harmful radiation, maintaining the protective shield that would eventually allow life to leave its ancestral home in the oceans. Earth had become an oxygen world, a planet where energy was abundant and biological possibilities were limitless. The transformation was complete, but the story it had made possible was just beginning to unfold. In the oxygen-rich seas beneath that blue sky, life was preparing for its next great adventure, building the cellular and developmental machinery that would eventually fill the world with the complex, multicellular organisms we recognize as typical life today. But for now, it was enough to breathe, to let oxygen flow through microscopic respiratory systems, powering the metabolism of cells that had learned to turn a deadly poison into the fuel of life. The blue-green rebels had won their revolution, and Earth would never be the same again. The revolution had succeeded beyond anything its microscopic architects could have imagined. What started as a simple metabolic innovation had become a planetary transformation that reached into every corner of Earth's system: the atmosphere, the oceans, the rocks, the sky. All bore the chemical signature of that ancient biological rebellion. and the rebels themselves. The cyanobacteria that had started it all were still there, still photosynthesizing, still producing oxygen, still building their layered stromatolite communities in the shallow seas. They had become the foundation of a new world, the bedrock upon which all subsequent life would build its increasingly elaborate structures. Their legacy was written in the blue of the sky, the red of iron formations, the oxygen in every breath. They had given Earth its atmosphere, its ozone layer, its chemical foundation for complex life. Most importantly, they had proven that even the smallest organisms could reshape entire worlds when they stumbled upon the right innovation at the right time. The great oxygenation event was over, but its consequences would reverberate through the rest of Earth's history. Every evolutionary innovation that followed, every organism that would ever breathe oxygen, every moment of complex life on our planet, all owed their existence to those ancient microbes that had dared to split water and change the world. The sky was blue, the air was breathable, and life was ready for its next great adventure. The stage was set for complexity, for size, for the kind of biological diversity that would eventually fill every corner of an oxygen-rich world. But that's a story for another time. For now, it was enough to marvel at what microscopic revolutionaries could accomplish when they put their minds to it. They had turned an alien world into home. They had painted the sky blue, and they had given every future organism the gift of breath. The evidence for this ancient transformation is written in stone, quite literally, scattered across every continent on Earth, in formations that tell one of the most extraordinary detective stories in geological history. And nowhere is this evidence more dramatic than in the banded iron formations, those distinctive striped rocks that look almost like geological zebra patterns stretching across ancient landscapes. Picture walking through the Pilbara region of Western Australia or the Iron Ranges of Minnesota and Michigan. You're looking at rocks that are 2.5 billion years old, and every single stripe tells a chapter of the story we've been following. The red bands are iron oxides, rust formed when oxygen met dissolved iron in ancient seas. The darker bands are silica-rich layers deposited when oxygen production slowed down. These aren't just pretty patterns, they're the fossilized remains of the greatest environmental transformation in Earth's history, preserved layer by layer like pages in a stone book. Each band represents cycles of cyanobacterial activity, seasons when these microscopic oxygen factories were working overtime, followed by quieter periods when production slowed. The scale of these formations is mind-boggling. We're talking about deposits that stretch for hundreds of kilometers and contain billions of tons of iron that was pulled directly out of ancient seawater by biological activity. The Hamersley Basin in Australia alone contains enough iron ore to supply human civilization for centuries, and every atom of that iron was precipitated by oxygen produced by organisms you'd need a microscope to see. But here's what makes the banded iron formations truly remarkable as evidence. They appear in the geological record right around 2.7 billion years ago, exactly when we'd expect cyanobacteria to have been ramping up their oxygen production. They continue forming for nearly 1 billion years, documenting the long struggle between oxygen production and consumption that characterized the Great Oxygenation Event. Then, around 1.8 billion years ago, they suddenly disappear from the rock record. Not because cyanobacteria stopped producing oxygen, but because there was no more dissolved iron left in the oceans to precipitate. The chemical sinks had finally been overwhelmed, and oxygen was free to accumulate in the atmosphere without being immediately consumed by iron reactions. The timing of this disappearance marks what geologists consider the true end of the Great Oxygenation Event. From that point forward, oxygen levels could rise more steadily toward the concentrations that would eventually support complex multicellular life. The banded iron formations had done their job, serving as massive chemical buffers that regulated the pace of atmospheric change. But the iron formations aren't the only evidence preserved in ancient rocks. Paleosols, Fossilized soils from before the oxygenation event show clear signs of chemical weathering that could only occur in oxygen-poor environments. These ancient dirt layers contain minerals like pyrite and uraninite that are completely unstable in the presence of oxygen, but were perfectly preserved in the reducing atmosphere of early Earth. The contrast with younger rocks is stark. Red beds, sandstones coloured by iron oxides, begin appearing in the geological record right around the time oxygen levels started rising. These red rocks could only form when iron-bearing minerals were exposed to oxygen-rich weathering, creating the rusty coatings that give them their distinctive colour. It's the same process that creates rust on your car, but written large across entire geological formations. The chemical signatures go even deeper. Sulfur isotopes in ancient rocks reveal the changing chemistry of Earth's atmosphere with remarkable precision. Before the Great Oxygenation event, sulfur isotope ratios show clear evidence of atmospheric chemistry dominated by volcanic gases and reducing conditions. After the event, these ratios shift dramatically, reflecting the new oxidizing environment that cyanobacteria had created. Even more subtle are the traces of noble gases trapped in ancient minerals. Xenon isotopes tell stories of atmospheric evolution that complement the sulfur data, providing independent confirmation of the timing and magnitude of atmospheric change. These chemical fingerprints are so precise that scientists can now date the Great Oxygenation event to within a few million years, remarkable accuracy for events that happened over 2 billion years ago. The biological evidence is equally compelling, though it requires more detective work to interpret. Stromatolites, those layered structures built by cyanobacterial communities, show up in the fossil record at exactly the right time to have been the oxygen producers we've been discussing. These formations become increasingly common and diverse throughout the period when oxygen was accumulating, then decline in abundance as more complex organisms evolved to compete with cyanobacteria. Modern stromatolites still exist in a few locations around the world, living fossils that give us direct insight into how their ancient counterparts might have functioned. At Shark Bay in Western Australia, you can still see cyanobacterial mats building layered structures, just like their ancestors did billions of years ago. These modern communities are actually producing measurable amounts of oxygen, tiny bubbles that rise through the water like microscopic breath. The preservation of these ancient microbial communities is nothing short of miraculous. We're talking about soft-bodied organisms with no hard parts, the kind of life forms that normally leave no fossil trace at all. But the stromatolites they built became geological monuments to their existence, rocky testimonials to the biological revolution that transformed our planet. The diversity of stromatolite forms tells us something important about early cyanobacterial evolution. Some grew as flat mats carpeting the seafloor. Others developed into towering columns several meters high. Still others formed branching tree-like structures that created underwater forests of living rock. This morphological diversity suggests that cyanobacteria were already experimenting with different growth strategies and environmental adaptations. But perhaps the most important evidence comes from the chemistry of the stromatolites themselves. Carbon isotope ratios in these ancient structures show clear signatures of photosynthetic activity, the same chemical fingerprints that modern cyanobacteria leave in their organic matter. This isotopic evidence provides direct proof that these organisms were indeed using photosynthesis to extract carbon from their environment. The geographic distribution of stromatolites also tells a story of global environmental change. These structures appear in shallow marine environments on every continent, suggesting that cyanobacterial communities were spreading across the planet's surface waters. The consistency of their chemical signatures indicates that the same basic biological processes were operating worldwide, a truly global phenomenon. As we piece together all this evidence, a remarkable picture emerges of biological innovation on a planetary scale. The Great Oxygenation Event wasn't just a local phenomenon or a gradual shift in atmospheric composition. It was a revolution that reached into every corner of Earth's system, leaving its mark in rocks, minerals, and fossils that we can still read today. The precision of this geological record allows us to reconstruct not just what happened, but how it happened. We can see the gradual buildup of oxygen-producing communities, the long period when chemical sinks absorbed their waste product, the tipping point when production finally overwhelmed consumption, and the cascading consequences that followed. Modern analytical techniques have revolutionized our ability to read these ancient stories. Mass spectrometry can detect trace amounts of isotopes that reveal atmospheric chemistry from billions of years ago. Electron microscopy can identify microscopic fossils preserved in rocks older than complex life itself. Geochemical analysis can reconstruct ocean temperatures, pH levels, and nutrient concentrations from chemical signatures locked in ancient minerals. This wealth of evidence has allowed scientists to test and refine theories about the Great Oxygenation Event with unprecedented precision. We can now say with confidence not just that the event happened, but when it happened, how long it took, and what its consequences were for life and environment. The story that emerges from this evidence is more complex and fascinating than early researchers ever imagined. The Great Oxygenation Event wasn't a simple linear increase in atmospheric oxygen. It was a series of advances and retreats, a planetary system learning to balance biological production with chemical consumption over hundreds of millions of years. Recent discoveries have revealed multiple episodes of oxygenation, temporary increases in atmospheric oxygen that occurred hundreds of millions of years before the main event. These early whiffs of oxygen show that cyanobacteria were experimenting with large-scale oxygen production much earlier than previously thought, but that various feedback mechanisms kept preventing permanent atmospheric change. The complexity of this process highlights something important about Earth as a system. This isn't just a story about biology or chemistry or geology operating in isolation. It's about the intricate connections between life, atmosphere, oceans, and rocks that make our planet a truly integrated system where changes in one component cascade through all the others. Understanding these connections has implications far beyond ancient history. The same biogeochemical cycles that regulated Earth's atmosphere billions of years ago are still operating today, still influenced by biological activity, still capable of dramatic change when pushed beyond certain thresholds. The Great Oxygenation Event shows us what can happen when a new form of metabolism evolves and spreads globally. It's a reminder that life doesn't just adapt to its environment, but actively shapes that environment, sometimes in ways that transform the entire planet. As we face our own period of rapid atmospheric change, driven by human activities, the lessons of the Great Oxygenation Event become increasingly relevant. We're seeing firsthand how biological activities can alter atmospheric composition on a global scale, how those changes can trigger feedback loops that amplify or dampen the original effects, and how the consequences can persist for geological timescales. But there's also something deeply hopeful about this ancient story. It shows us that life has a remarkable ability to innovate, adapt, and ultimately thrive, even in the face of dramatic environmental change. The organisms that survived the oxygen catastrophe didn't just endure the new conditions, they learned to exploit them, developing new metabolic strategies that were far more efficient than anything that had existed before. The same innovative capacity that allowed life to turn a deadly poison into the foundation of modern biology is still operating today. Evolution hasn't stopped, adaptation hasn't ceased, and the same creative forces that built the oxygen-rich biosphere we inhabit are still at work in every ecosystem on Earth. The evidence preserved in ancient rocks tells us that our planet has been through dramatic transformations before, and emerged not just intact, but more vibrant and diverse than ever. The great oxygenation event wasn't the end of life as it existed, but the beginning of life as we know it. Every red rock formation, every iron ore deposit, every chemical signature in ancient minerals bears witness to the power of microscopic organisms to reshape entire worlds. They remind us that the smallest innovations can have the largest consequences, that biological creativity knows no bounds, and that life will always find ways to not just survive, but flourish in the face of change. The story written in these rocks is ultimately one of transformation and possibility. It's proof that our planet is capable of reinventing itself, that life is endlessly creative in its responses to environmental challenges, and that even the most dramatic changes can ultimately lead to greater complexity and beauty. As we stand today, under that blue sky that cyanobacteria created, breathing the oxygen they produced, protected by the ozone layer their waste product formed, we're living testimony to the success of that ancient revolution. We are, quite literally, the descendants of that transformation, products of a world that learned to breathe and in doing so opened up possibilities that had never existed before. The great oxygenation event may have ended billions of years ago, but its legacy continues in every breath we take, every blue sky we admire, every moment of our oxygen-dependent existence. The revolution succeeded beyond anything its microscopic architects could have imagined, and we are still living in the world they created. The transformation that began with microscopic cyanobacteria wasn't content to stop at atmospheric chemistry. As oxygen levels stabilized and the planet settled into its new chemical reality, something extraordinary was happening beneath the waves. The very success of these oxygen-producing revolutionaries was setting the stage for biological innovations that would have been impossible in the ancient anaerobic world. By around 1.8 billion years ago, when the last of the banded iron formations were being deposited, Earth's oceans had fundamentally changed character. The dissolved iron that had given ancient seas their greenish tint was largely gone, precipitated out as those massive oxide deposits we can still mine today. What remained was something much closer to modern seawater, clear enough for sunlight to penetrate deeper than ever before. This clarity wasn't just an aesthetic improvement, it was opening up entirely new ecological real estate. Photosynthetic organisms could now thrive at greater depths, expanding the three-dimensional habitat available for life. The shallow, iron-rich puddles where cyanobacteria had first evolved were giving way to vast underwater prairies where different species could specialize in different light and nutrient conditions. The cyanobacteria themselves were diversifying in response to these new opportunities. Some species adapted to the bright, oxygen-rich surface waters, developing enhanced UV protection to survive in environments that would have been lethal just a few 100 million years earlier. Others moved deeper, evolving more efficient light harvesting systems that could extract energy from the dimmer blue-green wavelengths that penetrated farthest into clear water. But the most significant changes were happening among the organisms that had learned to live with oxygen rather than just tolerate it. Those early eukaryotic cells, powered by their captured bacterial partners, were beginning to explore possibilities that would reshape the biological world in ways even more dramatic than the original oxygenation event. Size was becoming a major frontier for evolutionary experimentation. While prokaryotic cells were typically measured in micrometers, some eukaryotes were pushing into size ranges that made them visible to the naked eye. These cellular giants weren't just scaled-up versions of their smaller ancestors. They were developing entirely new internal architectures to manage the challenges that came with increased size. Transport systems became crucial as cells grew larger. Simple diffusion, which had been adequate for tiny prokaryotes, couldn't move nutrients and waste products efficiently across the expanded distances inside giant cells. Some organisms developed internal currents, streaming patterns that actively circulated cellular contents. Others evolved specialized transport organelles that could ferry materials from one part of the cell to another. Structural support became another major challenge. Small cells could rely on water pressure and surface tension to maintain their shape, but larger cells needed more robust frameworks. Some eukaryotes developed elaborate internal skeletons made of protein fibers, creating microscopic scaffolding that could support complex three-dimensional cell shapes. Communication systems had to evolve as well. In a cell measured in millimeters rather than micrometers, chemical signals took much longer to diffuse from one end to the other. Some large eukaryotes developed internal signaling networks that could coordinate activities across their expanded cellular territories, primitive nervous systems operating within single cells. These innovations were laying the groundwork for something even more revolutionary: the evolution of multicellular life. When cells that had already mastered internal complexity began experimenting with external cooperation, the results opened up possibilities that single-celled organisms, no matter how sophisticated, could never achieve. The transition wasn't sudden or obvious. It probably began with simple aggregations, individual cells clustering together for mutual benefit without sacrificing their independence. Some of these early partnerships may have been temporary, forming only when resources were scarce or predation pressure was high. But gradually, some aggregations began developing more permanent associations. Cells started specializing in different functions, with some focusing on feeding, while others handled reproduction or defense. This division of labor created efficiencies that more than compensated for the costs of coordination and communication between cells. The first true multicellular organisms were probably simple affairs, sheets or filaments of identical cells that functioned as coordinated units. But even these basic forms represented a fundamental breakthrough in biological organization. For the first time in Earth's history, individual cells were sacrificing their autonomy for the benefits of group membership. The evolutionary advantages of multicellularity became apparent quickly. Larger organisms could dominate smaller ones through sheer physical presence. They could access resources that were unavailable to single cells, like food particles too large to be engulfed by individual organisms. They could also develop specialized structures for different functions, creating biological tools that increased their efficiency and competitive ability. Defense was another major advantage of multicellular organization. While single cells were vulnerable to predation by any organism large enough to engulf them, multicellular organisms could grow beyond the size range of most predators. They could also develop protective structures, tough outer layers that shielded internal cells from environmental hazards. But perhaps the most important advantage of multicellularity was developmental flexibility. Single cells are essentially stuck with whatever capabilities they inherit from their parents. Multicellular organisms, however, could differentiate their cells during development, creating specialized tissues and organs that performed different functions for the organism as a whole. This developmental complexity required entirely new genetic systems. Simple prokaryotic genomes designed to control the activities of single cells were inadequate for coordinating the development and function of multicellular bodies. Eukaryotes began evolving more sophisticated gene regulation networks, complex systems that could control when and where different genes were expressed during development. The evolution of these regulatory systems was perhaps the most crucial innovation in the transition to multicellular life. Without precise control over gene expression, multicellular development would be impossible. Cells need to know what type of tissue they should become, when they should divide or differentiate, and how they should respond to signals from other parts of the organism. By around 1 billion years ago, these genetic control systems had become sophisticated enough to support organisms with hundreds or thousands of cells organized into distinct tissues. These weren't the complex plants and animals that would evolve much later, but they were unmistakably multicellular, with cells that had given up their independence to become specialized parts of larger wholes. The fossil record from this period is frustratingly sparse, but the chemical signatures preserved in ancient rocks tell a story of remarkable biological innovation. New types of organic molecules begin appearing, complex lipids and proteins that could only be produced by sophisticated eukaryotic cells. Steran compounds, molecular fossils of advanced membrane systems, become increasingly common and diverse. More importantly, some of these early multicellular organisms were beginning to experiment with hard parts, mineralized structures that could be preserved in the fossil record. These weren't the elaborate shells and skeletons that would characterize later complex life, but they were the first tentative steps toward the kind of structural innovation that would eventually produce recognizable body plans. The ability to precipitate minerals was another innovation enabled by the oxygen-rich environment that cyanobacteria had created. Many biomineralization processes require oxidizing conditions, and the increasingly oxygenated oceans provided ideal chemical environments for organisms to experiment with hard part construction. These early experiments in biomineralization served multiple purposes. Some structures provided protection against predators or harsh environmental conditions. Others offered structural support that allowed organisms to grow larger or develop more complex shapes. Still others created specialized tools for feeding, locomotion, or environmental manipulation. Each innovation opened up new ecological niches and drove further evolutionary diversification. Organisms with protective shells could survive in environments that were too dangerous for soft-bodied forms. Those with structural supports could grow tall enough to access resources unavailable to smaller competitors. Species with specialized feeding structures could exploit food sources that others couldn't process. This diversification was creating increasingly complex ecological communities. The simple, relatively uniform microbial mats of earlier eras were giving way to structured ecosystems with multiple trophic levels and sophisticated species interactions. Predation, competition, cooperation, and symbiosis were all becoming important evolutionary forces. The development of these complex ecological relationships was driving evolutionary innovation at an accelerating pace. Arms races between predators and prey led to increasingly sophisticated attack and defense strategies. Competition for resources favored more efficient metabolic systems and more effective resource acquisition mechanisms. Cooperative relationships selected for better communication and coordination abilities. Sexual reproduction was becoming increasingly common and sophisticated among eukaryotic organisms. The ability to combine genetic material from two different individuals was proving to be a powerful tool for generating the genetic diversity needed to adapt to rapidly changing ecological conditions. Sexual organisms could evolve much faster than their asexual competitors, giving them significant advantages in competitive environments. The genetic recombination that sexual reproduction made possible was also facilitating the evolution of increasingly complex traits. Beneficial mutations that arose in different lineages could be combined in offspring, allowing favorable characteristics to accumulate much more rapidly than would be possible through mutation alone. By around 800 million years ago, Earth's biosphere was populated by diverse communities of single-celled and multicellular eukaryotes, many of them large and complex enough to be easily visible without microscopy. These organisms were engaged in sophisticated ecological relationships that included all the major types of species interactions we see in modern ecosystems. The stage was set for the next great evolutionary transition: the emergence of large, complex, multicellular organisms with sophisticated body plans and specialized organ systems. The basic cellular and developmental machinery needed for this transition was already in place, refined through hundreds of millions of years of evolution in the oxygen-rich world that cyanobacteria had created. But this transition would require one more crucial environmental change: oxygen levels, which had fluctuated considerably since the end of the Great Oxygenation Event, needed to reach concentrations high enough to support the energy-intensive lifestyles of large, active organisms. The metabolic demands of complex multicellular bodies would require oxygen concentrations approaching modern levels. That critical threshold was approaching. Geological evidence suggests that oxygen levels began rising again around 700 million years ago, climbing toward concentrations that could support increasingly sophisticated forms of life. The atmosphere that cyanobacteria had begun transforming over 1 billion years earlier was finally approaching the composition needed for the kinds of organisms we think of as typical complex life. The biological innovations of the preceding billion years had created a world ready for this next evolutionary leap. Eukaryotic cells with sophisticated internal machinery, sexual reproduction systems capable of generating rapid genetic change, multicellular development programs that could create specialized tissues and organs, and biomineralization technologies that could build structural frameworks and protective shells. All the components were in place for the explosion of complex life that would transform Earth's biosphere once again. The oxygen-rich world that cyanobacteria had created was about to give rise to organisms that would have been unimaginable in the ancient anaerobic seas, where the blue-green revolutionaries had first begun their planetary transformation. The revolution that began with microscopic cells splitting water molecules was approaching its ultimate expression. A world filled with plants and animals, complex ecosystems spanning from the deepest oceans to the highest mountains, and ultimately, the kind of biological diversity that makes our modern planet so remarkably alive. But that explosion of visible life was still in the future. For now, Earth's biosphere remained largely microscopic, populated by sophisticated but tiny organisms that were quietly preparing for the next great chapter in the planet's biological history. The foundations had been laid, the stage had been set, and the oxygen-rich atmosphere was finally approaching the concentrations needed to support the energy-hungry lifestyles of truly complex life. The blue sky that cyanobacteria had painted was about to witness the emergence of organisms that could appreciate its beauty, creatures complex enough to look up at that azure dome, and perhaps even wonder about the ancient microscopic revolutionaries that had made it all possible. The great oxygenation event was complete, but its legacy was just beginning to unfold. Every subsequent innovation in the history of life, from the first large animals to the eventual emergence of intelligence itself, would build upon the chemical foundation that those ancient blue-green rebels had created when they dared to split water and poison the world with their waste. They had given Earth its breath, and now that breath was about to support forms of life more wonderful and complex than anything the planet had ever seen. The revolution was over, but the story it had made possible was just beginning to reach its full, magnificent potential. The microscopic architects of our modern world had completed their greatest work. They had built a planet where complexity could flourish, where energy was abundant, and where life could explore possibilities that had been unimaginable in the ancient anaerobic darkness. The sky was blue, the air was breathable, and evolution was ready for its next great adventure. In the oxygen-rich seas beneath that blue dome, life was stirring with possibilities that would soon transform the world once again. But this time, the transformation would be visible, dramatic, and populated by organisms large enough to appreciate the beautiful blue sky that their microscopic ancestors had created through the simple act of learning how to breathe. To breathe. The numbers are breathtaking when you really stop to consider them. We're talking about oxygen concentrations that climbed from virtually nothing to levels that could sustain increasingly complex metabolisms over the course of several 100 million years. And as those concentrations approached the threshold needed for truly sophisticated life, something remarkable was beginning to stir in Earth's ancient oceans. Around 700 million years ago, the atmospheric oxygen that had been fluctuating for over 1 billion years began another dramatic climb. This wasn't just another temporary spike in the long history of oxygenation. This was the build-up toward concentrations that would finally cross the metabolic threshold needed for large, active multicellular organisms. The timing wasn't coincidental. By this point, the biological machinery needed for complex life had been refined through hundreds of millions of years of evolutionary experimentation. eukaryotic cells had mastered internal complexity. Sexual reproduction had accelerated the pace of genetic innovation, and early multicellular organisms had begun developing the developmental programs needed to build specialized tissues. But all of these innovations had been operating under an energy constraint. Even the most sophisticated early eukaryotes were still limited by oxygen concentrations that were well below modern levels. Their metabolisms, while far more efficient than anything in the anaerobic world, still couldn't support the energy demands of truly large, active organisms. That was about to change. Geological evidence from this period shows clear signs of rising oxygen levels, chemical signatures that indicate the atmosphere was finally approaching the composition needed for the next great leap in biological complexity. The stage was being set for what paleontologists call the Ediacaran radiation, the first appearance of large, complex, multicellular organisms in Earth's history. The organisms that would emerge from this transition were unlike anything the planet had ever seen. Instead of the microscopic cells and simple colonial forms that had dominated for billions of years, Earth was about to witness the evolution of creatures measured in centimeters and eventually meters rather than micrometers. These weren't just scaled-up versions of earlier life forms. They were fundamentally different kinds of organisms, with body plans that required entirely new solutions to the challenges of being large and complex in an aquatic environment. They needed circulatory systems to transport oxygen and nutrients throughout their bodies, structural frameworks to maintain their shapes against gravity and water pressure, and sensory systems to navigate and interact with their environment. The energy requirements for such sophisticated body plans were enormous compared to anything that had existed before. Every heartbeat, every muscle contraction, every neural signal required oxygen to power the aerobic metabolism that made such activities possible. Without the atmospheric oxygen concentrations that were finally being achieved, these innovations would have been metabolically impossible. The first hints of this transition appear in the fossil record around 600 million years ago. Strange, soft-bodied organisms begin showing up in ancient marine sediments, creatures with body plans unlike anything in the modern world, but unmistakably large and complex compared to their microscopic predecessors. These Ediacaran organisms, named after the Australian hills where they were first discovered, represent one of the most mysterious chapters in the history of life. Some looked like quilted discs lying on the seafloor. Others resembled fern, like fronds swaying in ancient currents. Still others had segmented bodies that suggested the beginning of bilateral symmetry and directional movement. What made these organisms possible wasn't just their sophisticated cellular machinery or their complex developmental programs. It was the oxygen-rich environment that cyanobacteria had spent over 1 billion years creating. Every breath these early animals took, every metabolic process that powered their growth and movement, depended on the waste product that those ancient blue-green revolutionaries had been pumping into the atmosphere. The diversity of Ediacaran life forms suggests that evolution was experimenting with multiple different approaches to large-scale multicellular organization. Some organisms developed centralized body plans with distinct head and tail regions. Others remained radially symmetrical, like living flowers anchored to the seafloor. Still others seemed to combine features from both strategies. But perhaps the most significant innovation was the evolution of active locomotion. For the first time in Earth's history, organisms were moving under their own power across significant distances. This wasn't the passive drifting of planktonic microbes or the slow growth movements of colonial forms. These were animals that could chase prey, flee from predators, and actively explore their environment. This behavioral complexity required neural systems of unprecedented sophistication. Simple reflexes and chemical responses weren't adequate for coordinating the activities of bodies with multiple organ systems and complex behaviors. Some Ediacaran organisms were probably developing the first primitive nervous systems, networks of specialized cells that could process information and coordinate responses across their entire bodies. The metabolic demands of neural tissue are particularly intense. Brain cells consume oxygen at rates far higher than most other tissues, and the evolution of even simple nervous systems would have been impossible without the high oxygen concentrations that were finally being achieved. The blue-green revolutionaries weren't just making large bodies possible, they were making intelligent behavior feasible for the first time in Earth's history. The success of these early complex organisms created new evolutionary pressures that drove even more dramatic innovations. Competition between large multicellular forms led to increasingly sophisticated survival strategies, more efficient feeding mechanisms, and more effective defensive adaptations. Predation became a major evolutionary force on a scale never before seen. While microscopic organisms had certainly eaten each other throughout Earth's history, the emergence of large mobile animals created entirely new types of predator-prey relationships. Some early animals developed the ability to actively hunt other organisms, while their potential victims evolved increasingly sophisticated escape and defense mechanisms. This evolutionary arms race drove innovation at an unprecedented pace. Predators evolved better sensory systems for detecting prey, more efficient locomotory systems for pursuit, and more effective capture mechanisms. Prey organisms responded with improved early warning systems, faster escape responses, and protective structures that could deter or deflect attacks. The fossil record from this period shows clear evidence of these escalating interactions. Some ediacaran organisms developed tough, resistant body walls that could protect against predation. Others evolved the ability to burrow into sediments, creating three-dimensional refugia that weren't available to surface-dwelling forms. But the most dramatic innovation was yet to come. Around 540 million years ago, oxygen levels reached concentrations that approached modern atmospheric levels. This crossing of the metabolic threshold triggered what paleontologists call the Cambrian explosion, one of the most rapid and dramatic evolutionary radiations in Earth's history. The organisms that emerged during the Cambrian period were unlike anything the planet had ever seen. They had hard shells and exoskeletons, complex sensory organs, sophisticated nervous systems, and body plans that established the basic architectural templates for most major animal groups that exist today. These weren't gradual modifications of existing forms. They were radical innovations that appeared in the fossil record with startling suddenness, as if evolution had been waiting for the right environmental conditions to unleash a torrent of creativity that had been building for millions of years. The trilobites that scuttled across Cambrian sea floors had compound eyes with hundreds of individual lenses, visual systems more sophisticated than those of many modern arthropods. The anomalocaridids that hunted in Cambrian seas were meter-long predators with grasping appendages and streamlined body plans that made them formidable apex predators. Early vertebrates began experimenting with internal skeletons, structural innovations that would eventually give rise to fish, amphibians, reptiles, mammals, and ultimately humans. The first primitive chordates, ancestors of everything with a backbone, were developing the neural architectures that would make increasingly sophisticated behaviors and eventually intelligence possible. All of these innovations depended absolutely on the high oxygen concentrations that cyanobacteria had made possible. The complex neural systems that powered Cambrian behaviors, the muscular systems that drove active locomotion, the metabolic processes that supported rapid growth and reproduction, all required oxygen-rich environments to function effectively. The Cambrian explosion wasn't just a biological phenomenon. It was the culmination of the atmospheric transformation that had begun with microscopic cyanobacteria over 2 billion years earlier. Every complex organism that emerged during this radiation was a testament to the success of those ancient blue-green revolutionaries. The diversity of Cambrian life forms was staggering. In a relatively short geological time span, evolution produced organisms with virtually every major body plan that would persist through the rest of Earth's history. The basic anatomical architectures of arthropods, mollusks, echinoderms, chordates, and dozens of other major groups were all established during this period. But perhaps the most significant development was the evolution of ecological complexity that approached modern levels. Cambrian ecosystems included primary producers, herbivores, carnivores, decomposers, and filter feeders, creating food webs with multiple trophic levels and sophisticated energy flows. These complex ecological relationships were possible only because of the energy abundance that aerobic metabolism provided. The high efficiency of oxygen-based energy production meant that ecosystems could support multiple levels of consumers, each extracting energy from the level below while still leaving enough resources to sustain the entire system. The success of Cambrian ecosystems created positive feedback loops that accelerated further evolutionary innovation. More complex communities provided more ecological niches for specialization, which drove the evolution of increasingly sophisticated adaptations, which in turn created even more opportunities for diversification. By the end of the Cambrian period, Earth's biosphere had been fundamentally transformed once again. The microscopic world that had dominated for billions of years was now supplemented by complex ecosystems populated with large, active, intelligent organisms, whose very existence depended on the atmospheric oxygen that cyanobacteria had created. The blue sky that had emerged during the Great Oxygenation Event was now looking down on a world that would have been recognizable to modern observers. Complex animals swam through oxygen-rich seas, their sophisticated behaviors powered by neural systems that required high metabolic rates to function effectively. But the story was far from over. The atmospheric foundation that cyanobacteria had built was about to support even more dramatic innovations. The colonization of land, the evolution of complex terrestrial ecosystems, the development of intelligence, and eventually consciousness itself, all lay ahead in Earth's future. Each of these developments would build upon the oxygen-rich environment that those ancient microscopic revolutionaries had created through their simple metabolic innovation. The waste product that had once been a deadly poison had become the foundation for every subsequent chapter in the story of life on Earth. The Great Oxygenation Event had ended billions of years earlier, but its consequences continue to reverberate through every aspect of biological evolution. The blue-green rebels had not just changed the atmospheric composition of their planet. They had created the chemical conditions that made intelligence, consciousness, and ultimately civilization possible. As oxygen levels stabilized at concentrations that could support the most energy-intensive forms of life, Earth was poised for its next great transformation. The colonization of terrestrial environments, made possible by the ozone layer that oxygen had created, would open up entirely new frontiers for evolutionary experimentation. Plants would evolve from aquatic algae, developing the structural innovations needed to support their bodies against gravity and the physiological adaptations required to extract water and nutrients from soil rather than seawater. These terrestrial primary producers would create the foundation for complex land-based ecosystems. Animals would follow, first as simple arthropods and eventually as vertebrates with sophisticated respiratory and circulatory systems capable of extracting oxygen directly from the atmosphere. The energy abundance of aerial respiration would make possible the evolution of warm-blooded metabolism, active lifestyles, and the neural complexity needed for advanced behaviors. But all of these future innovations would depend on the atmospheric oxygen that cyanobacteria had created during their ancient revolution. Every breath taken by every terrestrial organism, every moment of complex life on land, every thought processed by every intelligent brain would ultimately trace back to those microscopic blue-green cells that had dared to split water molecules and change the world. The sky was blue, the atmosphere was oxygen-rich, and life was ready for its next great adventure. The stage was set for the colonization of land, the evolution of intelligence, and ultimately the emergence of organisms capable of understanding their own evolutionary history. The blue-green revolutionaries had completed their greatest work. They had built a world where complexity could flourish, where energy was abundant, and where life could explore possibilities that had been unimaginable in the ancient anaerobic darkness. Their legacy lived on in every breath, every blue sky, every moment of consciousness that their atmospheric gift had made possible. The Great Oxygenation Event was ancient history, but it remained the foundation upon which every subsequent development in Earth's biological story was built. The microscopic architects of our modern world had succeeded beyond their wildest dreams, creating conditions that would support billions of years of evolutionary innovation and ultimately the emergence of beings capable of appreciating the beauty of the blue sky they had created. The beauty of the blue sky they had created. The revolution was complete, but its architects were far from finished with their planetary makeover project. As oxygen levels finally stabilized at concentrations that could support the most energy-hungry forms of life, those ancient cyanobacteria continued their relentless work, pumping out the waste product that had become the foundation of everything we recognize as complex life today. But here's where the story takes another fascinating turn. The same organisms that had accidentally triggered Earth's first mass extinction were about to enable something unprecedented. The colonization of an entirely new frontier that had been sterile and lifeless for billions of years. We're talking about the land surface itself, that radiation-blasted wasteland that had been completely uninhabitable since the planet formed. Remember that protective ozone layer we mentioned? By around 500 million years ago, it had finally reached sufficient density to filter out most of the harmful ultraviolet radiation that had been sterilizing the continents. For the first time in Earth's history, the surface of the land was becoming genuinely habitable real estate. The transition wasn't immediate or obvious. The first colonists were probably simple organisms, maybe cyanobacteria themselves, creeping up into tidal zones and establishing precarious footholds in environments that were still harsh by modern standards. But they were pioneers in the truest sense, the advanced scouts of life's greatest migration. These early terrestrial experiments faced challenges that their aquatic ancestors had never encountered. Water wasn't everywhere anymore. It had to be actively sought out, conserved, and transported throughout whatever body plan an organism possessed. Structural support became crucial too, because air doesn't provide the buoyancy that water does. Organisms had to develop entirely new ways of holding themselves up against gravity. But perhaps the biggest challenge was respiratory. Extracting oxygen from air requires fundamentally different physiological machinery than extracting it from water. The organisms that would eventually thrive on land needed to evolve respiratory systems that could interface directly with the atmosphere that cyanobacteria had spent billions of years perfecting. The payoff was enormous, though. Atmospheric oxygen concentrations were higher than dissolved oxygen levels in most aquatic environments. Organisms that could tap into this aerial reservoir had access to metabolic resources that could support incredibly active lifestyles, complex behaviors, and the kind of neural sophistication that would eventually lead to intelligence. Plants were among the first to really master terrestrial living. These weren't the towering forests we know today, but simple organisms that looked more like green carpets spreading across damp soil. They developed root systems that could extract water and nutrients from the ground, structural tissues that could support their bodies against gravity, and waxy coatings that prevented them from drying out in the alien environment of open air. More importantly, they brought photosynthesis to land for the first time. Just as cyanobacteria had transformed marine ecosystems by becoming primary producers in aquatic environments, these early land plants began converting sunlight and carbon dioxide into organic matter that could support terrestrial food webs. The impact on atmospheric chemistry was immediate and dramatic. Terrestrial photosynthesis was incredibly efficient compared to aquatic versions, partly because plants had direct access to atmospheric carbon dioxide rather than having to extract it from solution in seawater. Oxygen production ramped up to levels that had never been achieved before. During some periods, atmospheric oxygen concentrations may have reached 35% or even higher, well above the 21% we breathe today. This hyperoxic atmosphere supported forms of life that seem almost mythological by modern standards. Insects grew to enormous sizes, with dragonflies sporting wingspans of over 2 feet, and millipedes reaching lengths of 6 feet or more. The reason for these giant arthropods lies in the physics of respiratory systems. Insects don't have lungs like mammals do. Instead, they rely on a network of tubes called tracheae that deliver oxygen directly to their tissues. The efficiency of this system depends on atmospheric oxygen concentrations, and the hyperoxic conditions of the Paleozoic era allowed insects to grow much larger than would be possible in today's atmosphere. But it wasn't just insects that were experimenting with gigantism. The first forests were dominated by plants that dwarfed anything in the modern world. Tree ferns reached heights of 40 feet or more, and some early trees developed trunk diameters that rivaled modern redwoods. These weren't just scaled-up versions of smaller plants either. They were entirely new forms of life with structural innovations that had never existed before. Vertebrates were slower to colonize terrestrial environments, but when they finally made the transition, the results were spectacular. The first amphibians were essentially fish that had learned to breathe air, but they retained their dependence on aquatic environments for reproduction. Their eggs couldn't survive in the dry conditions of land, so they had to return to water to breed. The evolution of the amniotic egg was the breakthrough that finally freed vertebrates from their aquatic ties. This innovation, which appeared around 300 million years ago, created a self-contained aquatic environment that could develop on dry land. Reptiles were the first to master this technology, and it opened up terrestrial niches that had never been exploited before. But here's what's really remarkable about all these terrestrial innovations. Every single one of them depended absolutely on the atmospheric oxygen that cyanobacteria had been producing for over 2 billion years. The respiratory systems that powered giant insects, the metabolic processes that supported massive plant growth, the neural complexity that would eventually lead to intelligence, all required the oxygen-rich atmosphere that those ancient blue-green revolutionaries had created. The colonization of land also had profound effects on global climate systems. Terrestrial plants began influencing weather patterns through their effects on local humidity, temperature, and rainfall. Forests created their own microclimates, moderating temperature swings and creating stable environments that could support increasingly complex ecosystems. The carbon cycle underwent dramatic changes as well. Plants began extracting enormous amounts of carbon dioxide from the atmosphere, converting it into woody tissues that could persist for decades or even centuries before decomposing. During some periods, so much carbon was being locked away in plant biomass that atmospheric carbon dioxide levels dropped to concentrations that triggered global cooling and ice ages. These climate oscillations created new evolutionary pressures that drove further innovation. Organisms had to develop strategies for surviving extended periods of cold, drought, or other harsh conditions. Some evolved dormancy mechanisms that allowed them to essentially pause their biological processes until favorable conditions returned. Others developed migration behaviors that let them track suitable habitats as they shifted across the landscape. But perhaps the most important consequence of terrestrial colonization was the creation of entirely new types of ecosystems. Land-based food webs developed complexity that rivaled or exceeded their marine counterparts. Primary producers, herbivores, carnivores, decomposers, and parasites all found niches in terrestrial environments, creating intricate networks of ecological relationships. The diversity of terrestrial life forms exploded as organisms adapted to different habitats and climatic conditions. Desert specialists evolved mechanisms for conserving water and tolerating extreme temperatures. Forest dwellers developed strategies for competing for light in dense canopies. Grassland organisms became specialists in rapid growth and reproduction in seasonal environments. Each of these adaptations pushed the boundaries of what was physiologically possible, and each depended on the high energy yields that aerobic metabolism provided. The oxygen that cyanobacteria had been pumping into the atmosphere for billions of years was finally supporting the kinds of complex, energy-intensive lifestyles that we associate with advanced life forms. By around 200 million years ago, terrestrial ecosystems had achieved levels of complexity that approached modern standards. Dinosaurs dominated many environments, displaying behavioral sophistication that required significant neural resources. Some species developed complex social behaviors, elaborate courtship displays, and parental care strategies that demanded considerable metabolic investment. The respiratory and circulatory systems that supported these active lifestyles were marvels of biological engineering. Some dinosaurs developed air sac systems, similar to those found in modern birds, respiratory innovations that maximized oxygen extraction efficiency and supported the high metabolic rates needed for active, warm-blooded lifestyles. But the story was still far from over. The atmospheric foundation that cyanobacteria had built was about to support even more remarkable innovations. The evolution of flight, which appeared independently in insects, pterosaurs, birds, and bats, required metabolic capabilities that pushed aerobic respiration to its absolute limits. Flying organisms need to maintain incredibly high metabolic rates to power the muscle contractions that generate lift and thrust. The energy demands of flight are so intense that it's only possible in atmospheres with substantial oxygen concentrations. Without the oxygen-rich environment that cyanobacteria had created, flight would have been metabolically impossible. The mastery of three-dimensional movement through the atmosphere opened up entirely new ecological niches and evolutionary possibilities. Flying organisms could exploit resources that were inaccessible to terrestrial forms, escape from ground-based predators, and colonize isolated habitats like islands and mountaintops. More importantly, the evolution of flight facilitated the development of increasingly sophisticated navigation and sensory systems. Organisms that moved rapidly through three-dimensional space needed precise control over their movements and detailed awareness of their environment. This drove the evolution of enhanced visual systems, improved spatial processing capabilities, and more sophisticated neural integration. The cumulative effect of all these innovations was the creation of biospheres with unprecedented complexity and diversity. By the time mammals began diversifying after the extinction of non-avian dinosaurs, terrestrial ecosystems supported thousands of different species with intricate ecological relationships and sophisticated behavioral repertoires. But perhaps the most remarkable development was still to come. The energy abundance provided by aerobic metabolism in oxygen-rich environments was about to support the evolution of neural systems, complex enough to generate consciousness, intelligence, and ultimately the capacity for understanding the very evolutionary processes that had created them. The primates that would eventually give rise to humans were developing brains with metabolic demands that approached 20% of their total energy budget. These energy-hungry neural systems could only function in environments with abundant oxygen and efficient respiratory systems capable of meeting their intense metabolic requirements. Every thought, every moment of consciousness, every flash of insight that would eventually allow humans to decipher their own evolutionary history depended on the atmospheric oxygen that cyanobacteria had been producing for over 3 billion years. The waste product that had once triggered Earth's first mass extinction had become the foundation for intelligence itself. As human civilization developed and eventually created technologies capable of studying ancient rocks and reconstructing Earth's early history, those technologies too depended on the oxygen-rich atmosphere that enabled complex life. The steel in scientific instruments, the combustion engines that powered research expeditions, the metabolic processes that fueled scientific thinking, all traced back to the atmospheric transformation that began with microscopic blue-green cells learning to split water molecules. Today, as we stand under that blue sky that cyanobacteria painted and breathe the oxygen they produced, we're living testament to the success of their ancient revolution. Every breath we take connects us directly to those pioneering organisms that dared to poison their world and accidentally created ours. The Great Oxygenation Event wasn't just a chapter in Earth's ancient history. It was the foundation for everything that followed, the chemical transformation that made complexity, intelligence, and ultimately civilization possible. The blue-green revolutionaries didn't just change their world. They created the conditions that would eventually allow their planet to understand itself. The revolution that began in microscopic cells over 3 billion years ago continues today in every photosynthetic organism, every oxygen-breathing animal, every moment of conscious thought that their atmospheric gift has made possible. They gave Earth its breath, and that breath became the foundation for every wonder the planet has ever produced. The sky is still blue, painted by the same oxygen molecules that power our metabolism. The air is still rich with the waste product that ancient cyanobacteria couldn't have imagined would become the foundation of complex life. And somewhere in the oceans, descendants of those original revolutionaries are still quietly doing what they've always done, splitting water molecules and releasing oxygen into an atmosphere that continues to support the most remarkable experiment in complexity that our planet has ever undertaken. The Great Oxygenation Event ended billions of years ago, but its legacy lives on in every breath, every blue sky, every moment of the oxygen-dependent existence that those ancient microbes made possible. They built a world where complexity could flourish, and that world is still flourishing today, still breathing the breath that blue-green revolutionaries gave it so very long ago. Long ago. So here we are, billions of years later, standing under that same blue sky that microscopic revolutionaries painted with their waste product. Every breath you've taken while watching this video, every moment of consciousness that allowed you to process this story, every beat of your oxygen-hungry heart, all of it traces back to those ancient blue-green rebels who dared to split water molecules and accidentally built the world we call home. The Great Oxygenation Event wasn't just ancient history. It's the foundation of your existence right now. The steel in your phone, the oxygen in your blood, the ozone layer protecting you from radiation, the very capacity for complex thought that let you understand this story. It all began with cyanobacteria, learning to breathe in a world that had never breathed before. Think about that the next time you look up at a clear sky. That brilliant blue isn't just beautiful. It's a monument to the most successful biological revolution in Earth's history. Those tiny organisms didn't just survive their own environmental catastrophe. They turned poison into possibility, death into life, and an alien world into home. The blue-green revolutionaries gave Earth its breath, and that breath became everything. From the first complex cell to the emergence of consciousness itself, every innovation built upon their atmospheric gift. They proved that even the smallest organisms can reshape entire worlds when they stumble upon the right innovation at the right time. The revolution is complete, but the story continues. Every day their descendants still quietly split water molecules in oceans and forests around the globe, maintaining the atmosphere that makes our existence possible. The sky is still blue, the air is still breathable, and life continues to explore possibilities that those ancient pioneers made real when they dared to change everything. They built a world where complexity could flourish, and we're still living in that world today, still breathing their gift, still benefiting from the most remarkable transformation our planet has ever seen. The Great Oxygenation Event ended long ago, but its legacy lives on in every breath, every blue sky, every moment of the oxygen-dependent miracle we call life.